Okay, this is going to be a short tutorial on how to draw the solid dash wedge format. Feel free to take notes. At this point, you should feel comfortable with Vesper shapes. So when I say, tetrahedral, you picture the correct thing. What this is going to teach us to do is this is going to teach us how to draw three-dimensionally. Because so far, when we've been thinking about tetrahedral, you've just kind of had to visualize it on the paper. But there's actually a method that teaches how to represent things three-dimensionally on a two-dimensional plane, namely on a piece of paper. So there are three different lines that we use. The first one that we use is a solid line, just a regular like you're drawing a line on a piece of paper. That represents any bond in the plane, specifically in the plane of the paper. The second one, the dash, and this can kind of point any direction. I'm going to draw it kind of coming out this way. And it's a solid, so I'm going to color it in. Oh gosh, no, I'm kidding. Sorry, that's a wedge. I got myself all mixed around. I'm drawing a wedge right now. This is a wedge, so it is a solid line. And in this case, I'm imagining an object kind of zooming out and towards the right. So picture as if this was a line drawn three-dimensionally, and probably neater than I've drawn it here. So this one represents a bond coming out towards you. The last one, again, I got myself all turned around here. The last one that we use to represent three-dimensionality is a dashed line. So that looks something like that. Sometimes you'll see it shaped like a wedge line. You'll see it kind of very dramatically drawn like that, but it does not have to be. This represents a bond. The word that we often use or that you'll hear is retreating, so it's going away from you. A bond retreating away from you. So these are the notations. Now let's see this thing actually in action, because that's when it starts to make sense. We're going to consider three different Vesper shapes. We're going to consider tetrahedral. We're going to consider trigonal pyramidal, and we're going to consider trigonal planar, because we kind of get to see all of these in action. The first one is tetrahedral. So if you can picture kind of how tetrahedral is shaped, I'm going to draw it first in more of a ball and stick model. So remember you have your central atom, and tetrahedral, tetra means four. So we actually have four kind of zones coming out from this central atom, and to orient themselves as far apart from each other as possible, they assume, I think it's 109.5 degrees. And what you end up with is you end up with one going straight up, and then you kind of have some kind of going back a little bit, and then you have one kind of coming out this way a little bit, and then you have another one maybe going back. So the limitations with drawing it this way is that unless you're really good at shading or something like that, it's not possible to really show the three-dimensional shape if you can kind of picture that tetrahedral structure in your head. So what we do is we introduce this solid dash wedge format. Now, one thing I'm going to tell you is that with the tetrahedral structure, you always put two solids, meaning two solid lines, next to each other. Put two solids next to each other, and I'm going to show you what that means here in a second. So we're going to try it again with that tetrahedral structure. We have our central atom. This time I'm going to start using these three notations up here. I'm going to say that the bond going up at the top, this one right here, is in the plane of the paper. Now, what does that mean? It means if I was hunkering down eye level with this molecule, that bond wouldn't be coming towards me, and it wouldn't be going away from me. It would just be in the plane. So I would draw that like this. I would also, now this is where things get a little tricky, because depending on how you orient yourself looking at this molecule, these bottom three bonds could be going a variety of directions. What we do is we make it easy on ourselves, and this is where this little rule right here comes into play. Put two solids next to each other. I am going to pick one of these three kind of arrowed bonds down here, this one, or this one. I'm going to pick one of those to be solid. It does not matter which one, but I'm going to put those two solids next to each other. And when I say next to, not right next to each other, but they will be neighbors. Notice how I still honor the bond angle, right? If I drew it like this, 90 degrees, that is not correct. So make sure that you do not do that. Honor the bond angle and honor the tetrahedral structure. These other two lines down here, I haven't accounted for these molecules yet, or these atoms, and so that's what I'm going to do now. I'm still going to honor the shape and kind of these angles that are already built into the molecule. I'm still going to keep those, but what I'm going to do is I'm going to take, let's start with this one over here. I'm going to take that. If I was, again, hunkering down eye level with that molecule, that atom would be retreating away from me. That would be the example of a dash. So notice I'm drawing it at the same angle, but there's that little dashed line. It's saying that it's going away from me. This one down here will be our wedge. If I was eye level with it, that would be coming towards me. So this is how we would represent it. If this was a molecule like methane, like CH4, how you would see that represented. You would have the carbon in the middle, hydrogen, boop, imagine that H looks good, hydrogen, and then we'd have H, and then here's my wedge with another H. It would be wrong if you drew it like this. Hang on, let me extend my page here. It would be wrong if you did this. If you did carbon, hydrogen, hydrogen, wedge coming straight, dash going right to the side. You see how I've just made it kind of almost look like a compass, like there's one up, one to the side, one down, and one to the other side. That is not correct. I still need to show that tetrahedral structure, but now I'm just using the solid dash and wedge lines to give it a little more detail. Let's look at trigonal pyramidal next. So this would be one, just to remind you, NH3, ammonia, is a great example of a trigonal pyramidal. This one we would have, to draw the Lewis dot structure, we'd have nitrogen, 3, 4, 5. We'd have a hydrogen here, a hydrogen here, and a hydrogen here. So to convert that into the kind of Vesper shape, its electron kind of geometry, if we include the electrons, would look like we'd have the N, and up here kind of coming out at the top, we'd have those two electrons. We'd have hydrogen kind of coming out this way, then we draw it. I'm kind of repeating what I did with the tetrahedral. So again, we're showing the shape, but it could be clearer, and we're going to do that using the solid dash wedge. I'll tell you right now, there are a couple ways to do it. Imagine if you had that little molecule sitting on the desk, you could kind of spin it, and depending on how you orient it, you could draw it slightly different ways. So if you kind of come up with something different than what I'm drawing, please note that that is not incorrect. So what we would have would be, one way to do it is I could draw the nitrogen. Now I'm moving into the molecular structure, so I'm not including the electron pairs anymore. One way I could do it is I could have one solid hydrogen. Notice how I'm still honoring the bond angles. One dashed hydrogen, and then one wedge hydrogen. Notice how, just like before, it would be wrong if I did nitrogen, hydrogen, coloring that in, hydrogen, hydrogen. That would be incorrect. I still have to honor that three-dimensionality that I'm showing here. Okay, last example that I want to show you is a trigonal planar. These are fewer and farther between, but it's still a really great way of thinking about it. For trigonal planar, one example would be, we looked at carbon bonded to a sulfur, hydrogen, and a hydrogen. So this is an example. There are three areas of kind of electrons. Everything is bonded, so there are no electron pairs like we had in the trigonal pyramidal. But what we do need to account for are these three areas here, represented by two hydrogens and one sulfur. So initially, this one, it's kind of nice and easy. If I were to draw this kind of electron density picture like I did over here, I'd end up with a carbon and a sulfur, and these hydrogens will angle themselves. Notice nothing is 90 degrees. Everything is kind of oriented 120 degrees. Imagine if you had a pizza and you cut it into three equal, really big slices, or like a pie and you cut it into big slices. That's what's happening here. So in this case, everything is on the same plane. If I was to place this molecule flat on a desk, I could look at it, nothing would be coming towards me and nothing would be going away from me. Everything would be straight up and down. So this is a case where the solid dash wedge requires neither a dash nor a wedge. It is just simply its own sort of Lewis dot structure, because nothing in the picture is going away from me and nothing in the picture is coming towards me. The solid dash wedge format can be applied to every Lewis dot structure and kind of three-dimensional molecule that we talk about in this class. So for the coming weeks, when we talk about drawing molecules, you will be drawing them using this format.